Okay, so now let's look at gate driver. Two things, one is non-overlap, clock generator plus your gate buffer. Okay, why do we need gate buffer here? Because your FETs are very large, and we know those caps will be like 10-20 picofarad kind of thing, even, or maybe even more. So in order to drive that such a large cap, you need a buffer. I mean, not a smaller inverter cannot drive that, because the rise and fall time we are looking here order of 1 to 2 nanosecond kind of thing. So if this is your power stage VDD, so what you have here is, these are buffers, and then before this you have non-overlap. Clock generator, and you feed your VPWM here, and this will be again running in the same VDD and ground. Okay, and this guy will also be VDD, ground, VDD, ground. Okay. So the first thing you have to look into, how do we design the buffer? Yeah, so what you do actually, so if let's say if this is let's name it, if this node is called VGate P and this is called VGate N. VGate P, and then we have VGate N. Okay. So basically, so one gate should turn on only when the other gate is turned off after that, and that's what we define as non-overlap time or your dead time. on overdrive per dead time, and that you have in both the sides. So this is rising and falling. So if we talk about let's say T fall, T rise, so your T fall and T rise usually order of 1 to 2 nanosecond if you are looking at 10 megahertz kind of frequency. Okay, you cannot afford very large, and your T dead also 1 to 2 nanosecond. So now this FET, if this is your buffer means you have two inverters, then you have another inverter, this is your C gate P, and now let us say assume this is 25 picofarad. So in order to drive 25 picofarad, so it will have some RC time constant. So when this inverter turns on, so what, let's say I am looking for 1 nanosecond. So if T rises and T fall equal to 1 nanosecond, what kind of RC time constant we require? So if we are measuring at, let's say 10 to 90%, so 80% of that, so how many time constant it will require to reach to 80%? 5 time is 95, or like pretty close to 100. So this will require maybe roughly 3 RC, okay, or 2 to 3, yeah. So which means 2 to 3 RC time constant, you are closer to 1 nanosecond. So RC will be how much? Let's say closer to 0.5 nanosecond. C already known, and R will be the, so this is your buffer, inverter buffer, and this is nothing but this guy. Okay, when we say RC is basically nothing but R on multiplied by C gate P. So from here you know what kind of size you will require. Okay. So this is the one way you can calculate. Other way you just simulate and find what size of inverter you will require with a 1 or 2 nanosecond kind of a rise time. Now once you have that, this device is also big, huh? Big devices. So it will have its own cap again. So the previous one also should be capable of driving that. So this may be like maybe order of 1 picofarad or say, you can say. Okay. So in order to drive that, you have to find what size you will require again based on your RC time constant. Now, so now if I am looking at a 1 or 2 nanosecond here at the gate, that does not mean that each stage you can have 1 or 2 nanosecond. That will add lot of delay, and that will hamper all your non-overlap time, everything. So you have to make sure the previous stage should have a rise and fall looking like 100 picosecond or so. Okay. So whenever you are having a chain of these inverters here driving your so this will be the biggest, then you will have a smaller, then smaller. This is how it looks like. So the simplest way what you can do, because these inverters, I mean if you look at a characteristic, they will have a same characteristic. When I say they are built using the same devices, so when you are increasing the size, you know the gate cap is increasing. So roughly you can estimate one inverter in order to get 100 picosecond, what should be the next inverter which will be driven by the previous one, what size, 5 times of that or 10 times of that, and you can simply use that formula. And in the technology, so in the older years, if you pick up any textbook, he will say it's a factor of E. Okay, pick any old book like VLSI book, you will say they will factor, because in the old technologies, one inverter can drive with the factor of E, which is roughly 2 times of that of its own size. It can drive very easily without adding too much delays. Okay, but these days these technologies you may find like maybe 5 or more than 5 times also. So whatever size of this inverter, so let's say this is this guy is whatever size W by L, and this has some cap C gate P. So if I call it, let's say NX, okay, so this might be N by 10x, this may be N by 100x, something like that. Okay, and that's how it will keep reducing. So the most important thing you have to make sure, so the T rise and T fall, we are looking for 1 to 2 nanosecond, but here all these we are looking at T rise and T fall order of 100 picosecond. Okay, so which means the gates, the slew rate at the gate is mostly driven by the final inverter, and before that you are simply making sure that this whole chain should be able to drive the gate cap of each stage, and that's why you progress like gradually rather than simply putting a 2 or 3 inverters. Okay, so in some cases you may even require, let's say more than 5 or so. Okay, so it all depends on what kind of rise and fall time you are looking at each stage. This is only driving half cap, each inverter will driving both N and P, but the final inverter is driving only P. So you cannot say that whatever the size of this, and you can simply scale down. Okay, so you look at a cap here, but after that all the devices are same, both have a like complementary NMOS and PMOS. So they are because the gates are shorted, here the gates are not shorted. Okay, so that the same formula you cannot apply. That does not mean that this will become whatever the size of this and divide by 10 you can make. That may be even larger, maybe 50 times or so. Okay, whatever the size of this divide by 50, something like that. W by. Okay, so that's how you do, and then you have non-overlap clock generator. So let's see how we do that. So if you look at the logic here, I mean this is your V get P. So I am stretching this dead time just to make sure it's visible, but that does not mean that your dead time you can keep that high, because it will hamper your efficiency. So this is your V gate. So we know we have VPWM. So what does it mean? Which means when your PMOS is turning off or NMOS is turning off, you have to do right at the edge of your PWM. So when PWM goes high, which means you have to turn on PMOS and turn off NMOS. So you will immediately turn off NMOS at the rising edge of your PWM, but you will turn on PMOS after some delay. Same way, if your PWM is going low or at a falling edge, you want your PMOS to turn off immediately, but you turn on NMOS after some delay. That is how you introduce this dead time. Okay. So we have to build a logic where at the rising and falling edges, the devices will turn off immediately, but they will turn on after some delay, which means you need some kind of feedback to do that. So we get a VPWM, and then so this is my buffer. I am only drawing buffer here, and you can assume that this buffer is implemented using this chain of inverters. Okay. So now what I am looking, I know this is PMOS. When PWM is going low, I have to turn off or make it high. So what logic is applied there? Which kind of a gate will basically give you high, forcefully high when input is 0? NAND gate, huh? And then on the other side, this is your again buffer. You have NMOS and they are connected together. This is where you connect your LC. And we want these guys to go, the gate of this NMOS, this guy to go to 0 when VPWM is high. So when is high, I want to make it 0, okay, forcefully 0. You can say, okay, this can be done by using OR gate or NOR gate, okay. NOR gate, if you make 1, it will go 0, but then in the logic OR, when you do the feedback, that may go wrong. So that is why, but in this case, when the other input is, let us say 1, then it will only depend on the second input, and that is how you build the logic actually. So that is why we are using NAND and AND gate, so that when in the other case it only depends on your feedback signal. So all I need to do, place one inverter, and so when this goes high, this will go low, and this will forcefully make the gate 0. Now we have to look at this signal. So if this is going high, then this will go low, and I want to turn this on. So I know this will turn off immediately, PMOS, and I want to turn on this after some delay. So I know when both will be 1, output will be 0. So I have to make this other signal 1 after some delay. So if I take this signal, I know this is going 0, okay. So I have to make sure that this device has turn off completely when you are turning on this. So, and that can be told only by looking at the gate. That is why I am taking the feedback from gate, not from here. This is wrong. Okay, but if you look at any digital logic book or anything, they might be taking feedback from anywhere, because they are not driving such a huge gate. So the rise and fall time and delays looking at this gate node will be relatively same compared to the previous stages. So in that case, you can take the feedback before this buffer also, but here you know that the rise time fall time itself here is 1 nanosecond. So if you are looking at a, let's say your threshold inverter, this gate are tripping at VDD by 2, then half a nanosecond delay is added by this gate itself, gate rise and fall time. So that's why you have to make sure that you take the feedback from the gate at the end, from the end point. So and this is going 0 and we want this input to go high, so you connect an inverter here. Now when this is going low, what I want, this will go high immediately and I want this to go high. So this is going high and I want this also go high. So I don't need any inverter as such inversion, but since you have a delay here, in order to match that delay you have to add a inverter. So I require 2 because I want same polarity. So you have to divide the delays half. So if this is TD, then other should be 0.5 TD and 0.5 TD because we require 2 inverters. So 0.5 TD, 0.5 okay. So what will be the total delay here, I mean dead time per non-overlap time. So if you ignore the delays of stages before the buffer, okay. So one thing is you have to remember, you are measuring the delay from the gate, okay. So which means if there is a delay in this path, so the most of the contribution which is coming in the dead time will be from the rise time of this, okay. But if you are looking from a midpoint, then the major contribution will be from these feedback inverters TD. But if you are looking from let us say below half of VDD, so let us say you are looking very closer to 0, then you have to consider that 0.5 nanosecond delay from this, okay, because you do not know, I mean this inverter will be really tripping at VDD by 2 or VDD by 3 or VDD by 4. It is quite possible, I mean depending upon how these are sized, it may have a skewed threshold, okay. So that is how do, and you can basically change this TD to get to change your non-overlap time.